Good morning. So today we'll continue talking about electric potential, and again this is chapter 23 in your book. So these are again your reading assignments. I think I'll start with a reminder of these first three sections, and these are your suggested problems. Let me go ahead. First, we define electric potential in terms of electric potential energy. Since an electric field very much looks like a gravitational field, we can define electric potential energy exactly the same way we defined gravitational energy. I think a lot of things were similar. But we wanted to have a charge-independent formulation. So for that, we defined somewhat different concept, which we called electric potential. So electric potential was defined as the electric potential energy per unit charge. And since potential energy was defined with respect to a reference point, only the potential energy differences were meaningful. And here the same thing was valid. Only the electric potential differences were meaningful, okay? And due to the charge, we could obtain the electric potential energy in terms of electric potential by multiplying the electric potential with charge. For that, negative charges move towards high electric potentials and positive charges move towards low electric potential. That was something we had to remind ourselves. So we saw some examples and we emphasized that there was like more similarities between electric potential and potential energy. And for that, we started with definition of potential energy in terms of work done on a system. Change in potential energy in a system was equal to minus the work done on a system. And exactly this, in the same manner, we showed that we could define electric potential as the work done by the electric field minus the work done by the electric field in an electric field. And we showed a parallel plate example for this. And I think we solved this example for a charge conducting sphere. We knew the electric field inside was 0 and the electric field outside was falling with 1/r². And from this formulation, we calculated the electric potential of this charge sphere outside and inside. We found outside it was falling with 1/r, whereas inside it was constant. Okay. So we considered point charge to calculate the electric potential, and we find somewhat similar result. The electric potential for a point charge was 1/4πε0 Q/r, and where r is your distance, and we call this Coulomb potential. And we said if you have more than one charge, you could separately calculate electric potential contribution from each charge and add them up. Okay. Today we all do some examples on that line for the continuum charges. So then let's talk about this. Potential due to several point charges. We already talked that you could just calculate the potential for each charge and sum them up. This is like potential for charge Q1, potential for charge Q2. You can just separately calculate each one and then just do this algebraic sum all of these numbers. And if you have like a continuum charge, we know what to do. This integral will be replaced with this summation will be replaced with some integral, and you have to sum over all little charges in the continuum. So the important thing to notice here is like there's no vector information. So in the case of electric field, we had to deal with vectors, and we had to decompose vectors and calculate the components separately. Here, this whole thing is just one number, which is actually very nice. So we could just take the integral of this number and we are done. So here's the example. Maybe I can clean this up. So this is the potential due to a ring of charge. We are familiar with this system. We calculate the electric field of this system. Now let's think about its potential. So a thin circular ring of radius r has a uniformly distributed charge Q. And our task is to determine the electric field at a point P here on the axis of ring at distance x from its center here. So, okay, let me start. So I need to write potential, right? And for a point charge, we know potential is something like this, right? So there's like a point charge here, and I want to consider this point charge and it's write its potential here. Let me do this. Let me show this with dV is equal to, so the usual stuff, 1 over 4 pi epsilon naught. And I want to write this charge dq, and potential is charge divided by distance, and distance is already given here. So I'll just write it. So it's like x squared plus r squared. Good. So next I need to write dq. So basically this whole thing has a length, and there is like the charge density, let's call it lambda, is equal to total charge divided by its length. You know, it's like 2 pi r. And if you multiply this density with a little chunk dl, you are going to get total charge in this little chunk. But we know this dl is equal to, like, let's write it, pi r. dl is equal to r times d theta. Now we are familiar with this circle now. So these two r's cancel. For dq, we have something like q over 2 pi d theta. Okay. So let me just put this guy in. So let's show these cancellations. And so now I can integrate both sides. So if I integrate left-hand side, it's going to be v. If I integrate right-hand side, it's like 1 over 4 pi. So not integral, maybe I can even write this q over 2 pi integral d theta divided by x squared plus r squared from, let's say, 0 to 2 pi. Now the question is, how do I take this integral? Right? So maybe I can ask this way. Does x depend on theta? Right? So the variable we show with x is, right, whichever angle you choose, it is x, it's constant. So this one doesn't depend on theta. Does r depend on theta? No, right? R, whichever theta you choose, r is always r. So this whole thing is actually a constant. It just doesn't depend on my integration variable, which is theta. So I can just take this out. And what remains is like this d theta, but it's like an elementary integral. Integral of d theta is theta. And if the limits are 0 to 2 pi, the result will be 2 pi. So the result of this integral, 1 over 4 pi q, okay, this is epsilon naught, q, and divide this whole thing by x squared plus r squared. Okay, that's it. Maybe we can do one more example to see if we understand. So this integral stuff, I think you need to do a couple of times to get used to it. Let's do another example. And here's the, maybe I can delete this. Here's the most reasonable thing you can do. You have the ring, so you can sum of rings. And this is the question about that. Potential due to a charged disk. Previously, we calculated the electric field due to a disk. Now we are going to calculate the potential. And a thin flat disk of radius R0 has a uniformly distributed charge Q, as in this figure here. And we want to determine the potential at a point P on the axis of the disk, a distance x from its center here. Now I need to choose something I know. I know this ring here, right? And let me copy this result from here. For the ring, I have this. Copy. And let me paste. Okay? That's for a ring. Now I need to substitute what I have for Q here. So this Q, I need to know what it is on this ring. So let's do this exercise. This ring has a width. So this width, okay, maybe I can draw a ring like this. And I can draw a concentric ring, something like that. Right? So there is like a center somewhere. There is some radius R, and there is some width of this radius. This is, we call dr. And if I calculate the width of this dr with the circumference, which is 2 pi r, I get the area here. Maybe I can show it with here. This area here is what I need. Okay, so the, again, density times area is charge. So I'm going to get density times area is what? The R times 2 pi r. Okay. And the density is what? This is equal to total charge divided by total area, which is pi r squared. And I have dr 2 pi r. Now I can cancel this pi if I want to. Okay. So let's put this. So then this guy will go to dV, because this is a little contribution of the total potential, is equal to 1 over 4 pi, so not dq divided by x squared plus r squared. I know dq, I just calculated here. So let me put that and integrate both sides. If I integrate this one, I will get potential. If I integrate this guy, I get the mathematical expression for this. So V is equal to 1 over 4 pi epsilon naught. And this is an integral. And dq, I just found what? Q over r squared 2 times r times dr. I just wrote these things. Q r squared dr 2r, and what is left is just this guy. And so for here, the radius is also my variable, so I'll replace this with the little r, because this will change depending on where I am on the ring. So this is going to be 1 over x squared plus r squared. Now how do we do this integral? Maybe the first thing I can do is to detect what is not changing with the integral. So what is not changing, I can look, Q is constant, uppercase R, capital R is not changing. So I can take these guys outside the integral. So let me do this. This guy, let's take it outside. Let me push it here. Okay. So the integral I need to take is this guy. Maybe to be careful, I can also write the integral limits. So this R, which I actually showed with little r here. So a little bit, sorry about that. I changed the notation here. So little r goes from 0 to r naught. Okay. Now, how do I do this integral? What can I do about this? So also I need to ask, is x changing with integration variable r? Right? Is x changing as a function of r? No, right? So x is a constant, and the only integration variable is r, then that's my integration. What can I do about this? Change of variable, right? Substitution. Integration by substitution. Let's call u squared is equal to x squared plus r squared. So this one. So if I take the derivative of u squared with respect to u, I have u2 du. And if I take the derivative of this side, so this guy is constant, I don't care. That's the only one. So it's like then 2r dr. 2r dr. Then whenever I see x squared plus r squared, I will put u squared. Whenever I see u du, because these guys cancel, if you like. Whenever I see u du, I will put, whenever I see r dr, I will put u du. Right? So let me do this. This guy is, so 2, maybe I can take 2 outside too because I don't want to deal with this. So this is u du, and this is 1 over, okay, x squared plus r squared, so I put and u squared, okay? And my integral limits, if r is equal to 0, so this, I'll get u is equal to what? U is equal to x, and if r is equal to r naught, u is equal to square root x squared plus r naught squared. Okay. And now I want to look at this. U is a positive number, and square root of u is basically, okay, this square root will cancel with this, so why don't I do this, right? Let me do that. So this square root will cancel with this square, and now something nice happens. This guy will cancel with this guy. Again, I have some elementary integral, which should be what? Which should be u, and I just put the limits. It goes from x to x squared plus r naught squared. Now I'm done, basically. Here, I just come here and write the result. V is equal to 1 over 4 pi epsilon naught 2q over R naught. Sorry, this one is R naught. This is the density. So this one is also R naught, just to be consistent. So this guy is something like x squared plus R naught squared minus x. Okay. So, okay. So that's what the electric potential is. Now let's introduce something else. And I want to introduce so-called equipotential lines and equipotential surfaces. These are what their name suggests. These are like equipotential line or equipotential surface is a line or surface on which electric potential is the same at all points. Okay. Another way of saying this is the change of electric potential between any 2 points on an equipotential line or equipotential surface, let's call them A and B, should be 0, right? Remember that remember the definition of electric potential. It was E dot dl, and if we want to get electric potential difference between A and B, we can put it in the integral limits. It's like E dot dl. And if A and B are on the equipotential surface or equipotential line, this whole thing should be 0 because delta V should be 0. Then if E is not 0, there's the only way this can be 0 is this path you choose between A and B should be perpendicular to electric field. Okay? Then we get this important result. The equipotential lines or equipotential surfaces should be perpendicular to the electric field. Right? So let's just go to our like simplest example. If you have a parallel plate, let's say this is like an infinite parallel plate. Electric field lines are in one direction and they are uniform. And now we just said that equipotential lines should be perpendicular to the electric field. Here is your equipotential lines, it's green line. Here's another equipotential line. So these are all equipotential because the electric field is all the same here, right? So this is one equipotential line, this is another equipotential line, and so on, right? So another example is the point charge. If you have like a point charge, we know your potential at a given radius is constant. It's like 1 over r, right? And an equipotential surface here is like a shell that surrounds this whole charge. For example, this is one equipotential surface. This is another equipotential surface. Here's actually an example from your book. We can just exercise to warm up. And it says that for a single point charge with Q given charge, we want to sketch the equipotential surfaces or lines in a plane containing the charge. And we need to find the ones corresponding to V1 is equal to 10 volt, V2 is equal to 20 volt, and V3 is equal to 30 volt. Maybe I can do the one for 10 and you can do the others. We know V is equal to, maybe I can put K, Q divided by distance. And we are asked to find the distance, then R is equal to V over K times Q. And V is what, 10 volt divided by K. What was K? Does anybody remember K? So maybe I can write the first part, 8.99 times 10 to the 9, and the unit, exactly, right? And the unit is So Newton meter squared divided by Coulomb squared, and charge is 4.0 times 10 to minus 9 Coulomb. And what was the volt? What was the definition of volt? Does anybody remember what volt is? It's like a potential, and electric potential. And electric potential is electric potential energy per charge. So this should be joules per Coulomb. But joules is energy, and we know energy is what? Let me just push this just a little bit. Oops. But joules is energy, and energy is Newton times meter divided by Coulomb. So let's see if our units check. So I have Coulomb here, Coulomb square here, Coulomb here. Okay, this guy is gone. I have Newton here, this guy is gone. And I have meter here, I have 1 over meter. So, right, this is V, okay, then this is actually R to the minus 1. Here's the benefit of doing the checks, right? Then this is going to be the other way around. Then R is equal to 8.99 times 10 times 4.0 10 to minus 9, and divide this whole thing by 10, and this thing should be, okay, this is 10 to the 9 in meters. This is gone. This is like what? 8.99 times 4.0 divided by 10. It's like 3.5. All right. So this is the, okay, I think that's correct, right? So you should check for other like 20 volts and 30 volts and so on, right? Yes, good. So this was the equipotential for like parallel plate, these green lines, equipotential for a point charge, these spheric shells, and another example is like equipotential of a dipole. We know for a dipole is a system of two charges. One is positive, the other is negative, and electric fields start from the positive and terminate at negative. These are electric fields. And if you try to draw these green lines that are perpendicular to electric field, some of them close like this. Some of them are like this. Maybe they close, but at very large distances, okay? And there's like, in between, there's like a region in which potential is 0 and this line is straight, okay? So another interesting thing is like if you have metal, the entire interior region of a metal is an equipotential surface. Maybe it's like an equipotential volume, right? Because there could not be any potential difference within the metal. If there would be like charge flow and there would not be static equilibrium. So in the static case, entire metal should be an equipotential. So let's just focus on this dipole system, equipotential of a dipole a little bit more. And here is what a dipole is like. I now put like minus Q here, plus Q here, and I say they are separated by a distance L, and I want to find equipotential at a point P. And for this, I want to not find any P, but I want to find equipotential for P in which R is much, much larger than dipole separation, okay? So far, I just don't almost see these two charges at the same point, almost. Okay? And as usual, if, I mean, we almost always take V is equal to 0 at infinity, that's our reference point. Remember that for electric potential, we need to always specify a reference point. And for this infinite, R is equal to infinity is like 0. And now I can write each contribution separately. First, the positive charge, it's the usual stuff, 1 over 4 pi epsilon naught, Q over R. This is the distance. And the other one is, again, the same thing, charge goes to minus Q, but there's a little bit of distance difference, and I put it here. So one is R, the positive charge is R away from point P, and negative charge is R plus delta R away from this point charge. So I can multiply, I think I can take a common factor, 1 over 4 pi epsilon naught times Q, and then, you know, do this numerator, denominator's trick. If you do this, you get something like this, right? This is R plus delta R minus here R divided by R times delta R. So R is cancelled, and you have something like this, Q delta R. In the denominator, I have R times R plus delta R. Okay, now what do we do about this? Now we need to use this condition, R bigger than L. So if I use this condition, so these guys are almost identical. If you do a perpendicular, this guy is like, okay, this angle is almost 0, and this guy is almost perpendicular, and this guy is almost perpendicular, then I can find an expression for delta R in terms of this angle, and it's going to be, okay, this is almost theta 2, and this difference is like R times, what is it, cosine? Yes. So, sorry, L times cosine theta. So you can put that one here. This is L times cosine theta as here. Q is here. And for denominator, I just ignore this because there's like a large factor of R squared anyways. So I'll just put R squared. And if you look at this expression, we know QL. QL is the definition of P. Dipole moment. P by definition is equal to Q times L. Then the final expression is something like this. Okay. Does anybody remember the electric field of dipole? Maybe I can ask this. Compare with electric field E dipole, which was going like what? Yes, thank you. It was going like 1 over R cube. Here we have 1 over R squared. Yes, exactly. Okay. Here are some numbers. So, like I said, dipoles actually exist in nature. There are a lot of molecules that have like non-zero dipoles. Leading example is water, of course, and its dipole moment is something like this: 6.1 times 10 to minus 30 coulomb times meter. I think this is like hydrogen chloride. It is half, its dipole moment is half as big as water. This is like, this is ammonia, I think. And it's like dipole moment is comparable to water. These are some other molecules. If you are interested, you can look what they are. And okay, an interesting thing is, okay, so far how did we calculate the electric potential? So for example, here, okay, we know the electric potential of a point charge. Here we know the electric potential of point charge. And for the point charge, we calculated the electric potential from Coulomb's law, right? For example, here we said this is the definition of electric potential, and we put the electric field, which we knew to have this form, and we end up with this. Actually, we could carry out this program in the opposite direction. We could start with this Coulomb potential. For a point charge, we could say this is like 1/4πε0 Q over R0, and try to find electric field from the potential. And here is how we do this. We go back to the definition. Electric potential between 2 points A and B, which is VB minus VA, is equal to minus the line integral of electric field from A to B. Right? Then we could write this as like, okay, this is like VB minus VA is equal to VB, and we can write it as like an integral of dV from A to B. Then we can say, okay, this integral, this inside of integral should be equal to this inside of integral. Then we have something like this. dV is equal to dL times E. This is actually minus. Sorry. Oops. Should be a minus here. Right? And if we look at this, okay, you have some electric field. You have some electric field, something like that. And here you have some path. You want to go from A to B. And if you have like something like this, let's call this dL. Let's call this the component of maybe I can choose red here. So this is dL. I think electric field is something like this. So if you project E here, its component along L is EL, and that's the meaning of this dot product. And if you invert this one with this one, you get E of L. This component of E is first derivative with a minus. EL is equal to minus dV over dL. And we call this kind of expression a gradient. For example, I can decompose this L for each Cartesian components, X, Y, and Z, and I can get something like this. X component of electric field is del V del X, Y component of electric field is minus del V del Y, and Z component is minus del V del Z. Okay, this whole thing is called gradient. So the nice thing you need to notice here is like we can calculate V, which is just a scalar number, right? We can calculate it and take this program and find the electric field, which is a little bit simpler than doing these integrals and then decomposing and projection, that kind of painful calculation, because you only need to take the derivative here. Okay, maybe we can see this in practice a little bit. Here is the example from your book. Use electric potential to determine the electric field at a point P on the axis of A circular ring of charge, like this, and B, a uniformly charged disk, like this. Okay, maybe I can delete these. Let's see if this thing I just showed you is working. So here I just copied what we already obtained. The electric potential for a ring was like this, and electric potential of a disk was like this. And we are asked to find this is electric potential. We are asked to find the electric field. And we know the electric field, okay, E is equal to, okay, we are asked to find along X, so I will just put X, and it's going to be minus dV dx. That's all we need to use here. Okay. So this is what we obtained. Let's take the derivative. E of X is equal to minus dV V dx, it's equal to 1 over 4 pi epsilon naught Q. Now, how do I take the derivative? Okay, there is an overall minus. How do I take the derivative of 1 over square root? Simple, right? It's like 1 over 2, 1 over x squared plus r squared to the 3 over 2 times 2 times x. I can cancel this guy with this guy, this minus with this minus. And from here, I can already see electric field is 1 over 4 pi epsilon naught q x divided by x squared plus r squared to the power 3 over 2. Okay. Maybe you can go and compare with what we found last week. Maybe I can do this one too, the same thing. Ex is equal to minus dv dx is going to be equal to this whole, okay, minus this whole constant, q over 2 pi epsilon 0 squared. And I have to take the derivative of inside. Let me open the square bracket. This is going to be 1 over, okay, let me write carefully, 1 over 2, 1 over square root of x squared plus r0 squared. And I need to have two times x. So that's the derivative of first guy. And the derivative of second guy is simple, it's just minus 1. And I can cancel these two. So this guy is going to give me q over 2 pi epsilon naught 1 over r0 squared 1 minus something like x over x squared plus 0 squared. Okay. And let's check our result. So this is again compare with last week with last week. And we can check one limit. We know it's like, if you are really close to this guy, the electric field, what was it in terms of sigma? Does anybody remember? Electric field of a plane, sigma. Yes. Divided by 2 epsilon naught, right? Let's see if we can get that. So here, x should be really close. So 0. So I just put this guy to 0. The whole thing becomes like 1, something like this. Q over 2 pi epsilon naught 1 over r0 squared. But for here, I can see that this thing q over pi r0 squared is sigma. So this whole thing is equal to sigma over 2 epsilon naught. So it checks. Okay. All right. Now I think that's probably the last thing I need to introduce. And here is the electrostatic potential energy and electron volt. Now I want to calculate the electric potential energy of several charges. Maybe I can delete this and do it with you. Let me just delete this whole thing and delete this guy and see what we get. So let's start with one single charge. I have just one charge and nothing else. What is the electrostatic potential energy? If I have one charge, what is my potential energy? So that's electric potential, right? Electric potential and electric potential energy are different things. So if I have one charge, of course it has some electric potential, but the electric potential energy of the system is exactly like you said. It's like K, Q1, Q2 over R, but there is no Q2. What does that mean? Electric potential energy of a single charge is, I mean, in the universe, if I have only one charge, there's nothing, right? It's just zero. Now I want to put a second charge. Let me put this somewhere over here, and let me call this Q2, and let me also specify the distance between those two guys. This is like R, let's call this 1, 2. Now I have two charges, right? Now I can have potential energy, and the way we showed this was like, okay, we have like a single charge, and this single charge has some electric potential, and if you put another charge in the electric potential, another charge Q2 on that electric potential, you have a potential energy, and that's equal to what? Exactly what somebody else wrote a minute ago. It's going to be 1 over 4 pi, so not Q1, Q2 divided by R1, 2. All right. Now I want to put another one. Let's put, I don't know, to here, and let's call this Q3. Now what should I do? What is my total electrostatic potential energy? So if I put this guy, and if I get this one, I should do the same thing with this one, right? I put the radius R13, and I just open the parentheses, and this is going to be Q1, Q3, and I'll divide this whole thing with R13, right? That's it. What else? Exactly. There is also gonna be an electrostatic potential energy coming from these two guys, and we'll just put R23, and this is equal to Q2, Q3, divide this whole thing with R23, and now I can close the parentheses. That's all. So I think one last thing here I want to introduce is so-called electron volt. So the energy units is like what? What's the unit of energy? So far we used, maybe I can do a quiz. Yes, joules, right? So joules, which is equal to Newton times meter, is a very big unit for electric problems, because we are working with electrons, small charges, and this kind of like big energy is sometimes hard to deal with. For this, we want to define another unit, which is called electron volts. And electron volts is what its name says. Electron and volt, okay? Very simple to remember, electron and volt. Like an electron is what? An electron is a charge, and volt is volt. So if you multiply a charge with volt, that's electron volt. And let's calculate this in terms of joules. So we know electron volt, okay, this is, maybe I can delete this and ask you how we get this. So 1 electron volt is exactly what we said. It's like electron and volt. And what is the electron charge? Does anybody remember? 1.602 electron charge. Does anybody remember the electron charge? Actually, yes, times 10 to the minus 19 coulomb, and multiply this with volt, 1 volt, and you have yourself what? 1 electron volt. But I want to check this is indeed joules, so I want to write volt in terms of what? In terms of joules per coulomb, right? That's the definition of volt. This is coulomb, and if you simplify, you get 1 electron volt in 1 joules, which is equal to 1.602 10 to the minus 19 joules. All right, let's do an example and finish this class for today. And tomorrow we can solve problems. Okay, here. Calculate, okay, this is assembling a hydrogen atom. Calculate the work needed to disassemble a hydrogen atom. Assume that the proton and electron are initially separated by a distance equal to average radius of hydrogen atom in its ground state, which is given with this guy, and that they end up an infinite distance apart from each other. Okay, maybe I can draw a hydrogen atom for you and ask you what we can do. So, and the hydrogen atom is a positive charge. Okay, oops. Can do like this. A positive charge, and around this positive charge, there is some electron. And how do I separate these two guys? Or what is the energy that I need to separate these guys? So we need to write potential energy, right? U. And what is the potential energy? Somebody says it's K Q1 Q2 divided by, oh, it's R squared. R, right? Good. So this is R. Now, what is Q1 and Q2? One is positive E, charge of nucleus. The other one is minus E, charge of an electron. And then I have something like that. This is equal to minus K E squared over R. All right. Now let's calculate this and find. So K is like 8.99 times 10 to the minus. Okay, maybe I ask again so that you guys learn what is K. 10 to the 9. 10 to the 9. Okay, Newton meter squared divided by Coulomb squared. An electron charge is 1.602 times 10 to the minus 19, right? Times 10 to 1.602 times 10 to the minus 19. This is also Coulomb. This is Coulomb squared. And I divide this whole thing with the radius, which is given to be 5.29, 0.529 times 10 to minus 10 meters. And I want to write this, okay, if I do all these numbers, maybe I can show you, Coulomb, meter squared, meter, I'll get something in joules. but I don't want to get something in joules, right? I want to get something in electron volt. I just use this conversion, right? 1 electron volt is equal to 1.602 10 to the minus 19 joules. Then I can just drop one of these and write the result in terms of joules. So this is going to be minus 8.99 times, okay, let's also simplify these guys. You can tell this is minus 19 plus 9 minus 19, right? Minus 10, not plus 9 is 19, minus 19, they are gone. So this is going to be 1.602. Divide this whole thing with 0.529. Did I miss anything? And my unit is electron volt. Let's not multiply these numbers and see what they are. This is equal to minus 27.2 electron volts. So now, is that all? Is this all the energy I need to disassemble a hydrogen atom? Is there any other source of energy that I need to consider? Exactly, right? There's also some kinetic energy. And this guy is like not stationary, it's just like circling around this nucleus. Otherwise, it wouldn't be there, right? So how do I calculate the kinetic energy? So kinetic energy is equal to 1/2 v squared. How do I calculate this? What is V? Exactly, centripetal force, right? Like force, now I'll put K, Q1, Q2 is E squared divided by R squared. Now, the sign, I know it is going to be an attractive, so I don't get any trouble with signs. So this should be equal to V squared over R. So I can cancel these. And I can put, whenever I see mv squared, I can put k e squared over e. So this is equal to 1 over 2. Okay. This is equal to 1 over 2 k e squared over 2. But we just calculated this k e squared over 2. K e, okay, we just calculated this guy and found it like 27.2. So half of this is what this guy is. Let's divide the previous result with 2. So this is going to be 13.6 electron volt. So the total change I need to pay is U, or maybe I should write K first, K plus U, which is equal to minus 13.6 electron volt. Okay. Hopefully you guys remember this number. Does anybody remember this number from high school? Exactly, like ionization energy of hydrogen atom. All right. So I think that's it for me today. Maybe we can continue tomorrow with some problems.